Well, this chapter is a continuation of carboxylic acids. In particular, we'll talk about their derivatives. So to introduce some of these derivatives to you, let's take a look at this little table down here below. So starting off at the left, we have acid halides. So here we have usually a chloro group like an acid chloride. We have anhydrides. That's an O carbonyl and oxygen carbonyl. We've seen esters before. Those functional groups should be familiar with us. Amides we've seen. And nitriles we have seen also. So there's really only a couple groups in there that are new to us. Now, we're going to have to learn how to name all of these things. So chapter 21 is somewhat heavy in nomenclature as compared to some of the other chapters. Now we've seen some of that nomenclature in some of our problems that we've gone through the year, essentially. So let's take a look at how to name esters. Well, one way to synthesize esters is to do a Fischer esterification. So here we have a carboxylic acid here, plus an alcohol to give us an ester. Now, the way that we name the esters is that we name this part of the molecule here is a carboxylate. So just like it's a salt, like it had a charge. And then this is named as an alkyl group. Now let's look at an example down here below. So here we have methanol. It's really CH3OH, just kind of justified in a weird direction down there. But plus benzoic acid. So when we put those two things together, what we end up getting is an ester. So we get our benzoic acid part, that'll be benzoate. And then now the R group here is that, right, that CH3. So an O, CH3 there. So again, pointing out this part of the molecule here is going to be named as if it were an O minus. So benzoate. And then of course we know that that's a methyl. So then when we put those together, we get methyl benzoate. So fairly straightforward, right? Well, a couple of these molecules also can be cyclic, and they have their own special system of naming here too. So they're easy because the name is based on the open chain form. So the toughest thing is going to be taking a structure like this and opening it up back so that you can figure out what the open chain form was. So let's take a look at this cyclic structure over here. So first we notice that it's a carboxylic acid. It's 1, 2, 3, 4. So it's a bute, right? So we know it's a butanoic acid. And at carbon number 2 you have a methyl and a methyl. So it's a 2,2-dimethyl. Right, so we have a butanoic or butyric acid. We have a 2,2-dimethyl in there. And then remember that OH group, when it's part of a molecule that has a higher order priority functional group, then we call that a hydroxy group. So that's on carbon 4, so it's a 4-hydroxy. And no stereocenter there. So we put all that together and you get 4-hydroxy 2,2-dimethyl, and then butyric or butanoic acid. Okay. Now the ring over here on the other side, right, is 1, 2, 3, 4. It's a 5-member ring, so that oxygen right there is the 5th atom. It's the 5th atom that's in that ring. So when we name this thing, we just are going to add the word lactone to the end of it. All right, so they're called lactones. So it's pretty straightforward. Once we have that chain, then this cyclic structure would simply be 4-hydroxy, 2,2-dimethyl butanoic acid lactone. And that would be the full name of that structure. So when you're doing problems like this, one of the things you want to practice is taking this cyclic form and hydrolyzing it and opening it back up so that that becomes an OH, right? So that'll be an OH on this side, and then this side also will be an OH, right, from your carboxylic acid there. That's kind of how you think about that. So let's take a look at the nomenclature of amides. One way that amides can be made commercially really here is to have a carboxylic acid plus an amine under acidic conditions, especially with heat here. So heat is often used for that. And what you make is an amide. Now remember that nitrogen here is sp2 hybridized. Right, so it is in resonance, if you recall, with the carbonyl. Right, so you get your R O minus, and then your N H R plus. So because you have that sp2 character, you do have a little bit of restricted rotation around that nitrogen carbon bond. So when you look at your carbonyl nitrogen bond here, if this was your hydrogen in your R group, you'd have an equilibrium in essence with your carbonyl and your nitrogen, and that H and the R group switch. So you can see here's our R group, and it moved up to this top position. Here's the H, and it's moved down here to that bottom position. So the energy required to do that for that rotational barrier, it's about 75 kilojoules per mole, which turns out to be about 18 kcals per mole. So we have not pure double bond character, but some partial double bond character there. So carbon-carbon double bond is about 250 kilojoules per mole, roughly speaking, to do a rotation. You have to break that bond. Now, amides can be classified into primary, secondary, or tertiary, depending on the number of R groups that are attached to that nitrogen. So they're all going to have one, right? That's what makes the amide. So you have a primary, here you have a secondary, and then here you have a tertiary. Now, to name these, what we have to do is name the related carboxylic acid, and then we're going to replace the oic acid part with, or the ic acid part with amide. If we have R groups sticking off of our nitrogen, then they're in substituted. So down here below we have 1, 2, 3, 4, 5. So this would be pentanoic acid, but remember we said we're going to drop this oic part, so toss that, and then we're going to add amide. And then that is a methyl group there. So when we put all that together, that is N methyl pent and amide. Now, if we have a larger carbon chain with more substituents, then it's the same principle, it's the same idea. Right? So here, this is your carbon number 1, 2, that's a 3. So it's an N dimethyl, right? You got 2 of them. Then 1, 2, 3 hydroxy. And then how many carbons does this have? So 1, 2, 3, 4, 5, 6. So it's hex. It's an alkane. It's a hexane. It would be an oic acid, but we drop the oic and we add amide. So then putting all of that together, you're going to get, let's see, 3-hydroxy NN dimethyl hex and amide. So stereochemistry on that oxygen here, the carbon with oxygen, that's a number 1. Right, so you have your H back here, that's your number 4. This is your number 2, that's your number 3, so it goes that direction. 1, 2, 3. Looking at it like this, that is your S direction, and there you have it. That is the name of your amide. Now, we can also have cyclic amides. So cyclic amides are called lactams, and their name is going to be based on the open chain form of that molecule. So recognize that as being a cyclic structure, of course, and it's an amide. So that carbon, when this thing opens up, is going to grab a hold of an extra H, so that becomes an NH2. And then this carbon right here is in essence going to grab an oxygen. So it gets it from water when we open this thing up if we do a hydrolysis. So that's this guy right here. So when we name that compound, we have to name it as our open chain. So 1, 2, 3, 1, 2, 3, 4. So it's butanoic acid. So it's a but, N, right? Butene, oic acid. Now it's important here that we indicate that that's at number 2. So what we are missing in here is we need to put a 2 right in here. Right? So then when we put all of that together, this is but 2 enoic acid. And then off of our 4 group here is an amino. So 4 amino. And then the double bond has a cis or a Z indicator. Now it's easy when we go through and we put the name together here. We just copy that name. So it'll be a Z 4 amino but 2 enoic acid, and then we're going to add the word lactam here. So you get lactam. And that is how you name cyclic amides. Now we've seen nitriles before. We haven't learned how to name them yet though. So one of the ways that we saw that they can be synthesized is by hydrolysis. So we can have a nitrile under acidic or basic conditions here, and that'll make an amide, and then we can continue that reaction by adding heat here. With that heat, it takes us to a carboxylic acid. So naming these things is based on finding the longest carbon chain that contains that carbon triple bond of nitrogen. Now, that carbon is going to count in your parent. So it's not part of a substituent, it's part of the parent name. And then we add the suffix nitrile to the alkane name or the alkene name with no spaces in between. So looking down here below, here you have 1, 2, 3, 4, 5. So simply put pentane nitrile. Right? Down below, 1, 2, 3, 4, 5. So it's a pent, but we have a 3 ene nitrile, and then the stereochemistry on that is a Z. So Z pent 3 ene nitrile there. Now we've seen the mechanism of creating acid chlorides from carboxylic acids. One of the things that we're going to see shortly when we look at reactions is that acid chlorides are actually very reactive. Partly because you have a dipole getting pulled in 2 directions, which leaves a very large delta plus at that position. So we'll talk about that more a little bit later when we look at the reactions. Now as far as naming these things, well, we name the related carboxylic acid, and then what we're going to do is replace the ic acid with an "il" and then whatever that halide is. Most often we'll see that as being a chloride because we use thionyl chloride to make acid chlorides. So looking at this, we have 1, 2, 3, 4, 5, 6 carbons. So 6 carbons is hex. It'd be hexanoic acid. After that, we're going to drop the ic acid part, and we're going to add "il," and then it's chloride here for your halide. And then off of 1, 2, 3, 4, 5, that's a bromo. So then that is a 5-bromo hexanoyl chloride. And then we just have stereochemistry here. So that's your number 1. You have an H pointing back here, which is your number 4. That's your 2. That's your 3. So moving around that direction, that's an R. So you get an R here for that. Well, anhydrides of carboxylic acids can be synthesized a variety of ways. So we'll find out soon that most easily they're made with reacting a carboxylic acid with an acid chloride. Nonetheless, in the end, what we end up getting is a structure that looks like this. This is the functional group of the anhydride. So it pulls a dipole in 2 directions here. And again, that leaves a nice delta plus right here. So we'll see that these are reactive just like acid chlorides are, because you have a nice delta plus that's being pulled there. And the other thing that we're going to see is that the leaving group for acid chlorides and anhydrides are fairly stable compared to some of the other leaving groups in our carboxylic acid derivatives. Now, to name these, we're going to name each carboxylic acid half, and we're going to drop the word acid. We're going to put them in alphabetical order. So, alphabetical order, we're going to add the word anhydride there, and then if the 2 halves are the same, we're going to just write the name once. So here we have 1, 2, 3. So 3 carbons is prop, and if we name them as a carboxylic acid half, it'd be propionic acid. So because these are identical, it would be simply propionic anhydride. You could also call that propanoic too. And here, this part of the molecule is acetic. And then that part of the molecule here is propionic. So then putting those together, you would simply have acetic, propionic, and then add the word anhydride here. So if you're asked to draw the structure down below, you have to put together the 2 parts. So benzoic acid is this, and ethanoic acid is also known as acetic acid, right? But acetic acid has that structure. And in essence, those are going to combine just to form 1 oxygen there. So you would have that as your structure. So this could also be called acetic benzoic anhydride if you went with the acetic name rather than the eth name there. Well, now that we've had all that nomenclature, let's see how we put all these different concepts, multiple functional groups, all in one compound. So to do that, we have to be able to choose who the principal group is for the root name. And I'm going to create a little table over here on the side for you guys that you guys can consult as you're going through this chapter. So we're going to start off here at the top with the highest priority. So up here we have carboxylic acids. And as we go down, we have lower priority functional groups here. So next comes esters. After that, we have acid halides, right? In general, so acid halides are mostly, we'll see acid chlorides here. And then we have amides. nitriles next. Then we have aldehydes and ketones. Then we have alcohols. And then thiols. Amines. And then our doubles. And our triples. And then alkanes. Ethers. And then alkyl halides. So the way this works is that if you have an amide present in the molecule and there's also a nitrile, then the compound would be named as an amide, and then the nitrile would have to have a functional group name. So some of these things have functional group names. So nitriles, if we're part of a higher order functional group, if we contain a higher order on there, then these things are named as cyanogroups. Aldehydes, if you recall, those are formals. Ketones are oxo. Alcohols are hydroxy. Sometimes you'll see hydroxyl. Thiols are mercapto. And then amines are amino groups. Right? So then let's take a look at our example, see how we can put all that together. Well, here we have a carboxylic acid. So that's the winner. So when we look at our compound here, we are at the top of the chain. So everything below will be named as a substituent. So let's take a look and put this all together here for that compound. So let's go ahead and name this. So first thing that we need to do here is recognize that we have that carboxylic acid, right? We saw that before. So that it will be named as a carboxylic acid. So count them up. 1, 2, 3, 4, 5, 6, 7. So that means it's a hept. Right? It's not a heptane, it's a heptene. So 1, 2, 3, that's at 4, and that's at 5. So it's a hept 5-enoic acid. And then we have a 4-amino and a 4-hydroxy. So then that gives us a 4-amino, 4-hydroxy, and then hept 5-enoic acid, and then some stereochemistry to consider here. So that is that's going to be an E, right? Because our H's are on opposite sides here, right? So two identical groups, one on each carbon, opposite. That gives us E. Well, the last thing that you have to do here is look at the stereochemistry on that carbon. So remember, it goes carbon, nitrogen, oxygen, right on your periodic table. So oxygen is going to be our number 1. Nitrogen is our number 2. This side's our number 3, and this guy pointing back in plane's your number 4. What that means, though, is you have to look down this bond in order to figure out this direction correctly. So as you rotate that around, you'll find that this actually is S. So that gives you the S stereochemistry there. And guys, that concludes all of our nomenclature actually for organic chemistry. We're not going to really see any more nomenclature. So that was a lot, but congratulations, you are officially done with your nomenclature.